Good afternoon, ladies and gentlemen. The next talk, as you can see, is by Daniel Estévez, as it's written up there, EA4GPZ, GR satellites. That's the decoding of satellite data, telemetry, whatever. Daniel has got a PhD in mathematics, just to frighten you all. It is online, and yeah, okay, I won't say any more. Anyway, over to you, Daniel.
Yeah, thank you very much. It's a pleasure to be here, and it's a pleasure coming back to in-person conferences after COVID. So let's get started. I actually have a small introduction about GR satellites, which is one of my personal projects. It's a telemetry decoder for amateur satellites. And then I have some related experiments I have been doing throughout this year mainly. So GNU Radio. I guess a few of you in the audience are already familiar with GNU Radio. GNU Radio is an open source framework to do DSP for radio. This being the RSGB conference, I don't need to speak about what radio is, and DSP is digital signal processing. So having a CPU or having a GPU or an FPGA doing your radio modulations, decoding, whatever, GNU Radio is a tool which is going to be useful for that. So it comes with three things. It comes with a GUI application, which is called GNU Radio Companion, and in there you can build systems by dragging and dropping blocks on a canvas and connecting those blocks together. So think how you build one of these microwave radios. You have your mixer, you have your LNA, you have something, and you connect those with coax. So GNU Radio Companion is similar in that sense that you have we will see an example. You have a squelch block, you have an FM demodulator block, and you connect those with wires, so to speak. Besides that, there's a rich library of signal processing blocks that you can use, and those blocks can be as simple as sum, so sum together two signals, or they can be as complex as DVB-S2 modulator, so a complete transmitter for digital TV. And beyond that, you need some kind of engine or runtime to move data around, to decide what it's executed by the CPU, how to send data from one function to the other. So that's the GNU Radio runtime, and that releases the programmer from these kind of complications of dealing with buffers, with parallelism, so that you can concentrate on, I want to run and write my particular DSP routine inside this function. In the GNU Radio ecosystem, beyond GNU Radio itself, you also have a whole bunch of out-of-tree modules. So they are called out-of-tree modules because rather than being part of the GNU Radio source code tree, they exist outside of that, and you can think of them as plugins. They're intended to extend the functionality of GNU Radio beyond what's in tree. And there are many out-of-tree modules for many different applications. There are also full applications that use GNU Radio for the digital signal processing, and GQRX is one example. Maybe you've used GQRX. It's similar to SDR Sharp and all those applications. And there's also Q Radio Link, which is similar to GQRX, but also focuses on digital voice. And the idea here is you can do your GUI application or whatever application. Inside that application you need to do some signal processing, and you can't rely on GNU Radio to do the heavy lifting of the work. This is an example flow graph of how GNU Radio looks like. This is taken from the documentation, and this is a narrowband FM receiver for the 2-meter band. So you have a block here for the FunCube dongle. Then you have a low-pass filter for the signal. You also have this waterfall sync, which is plotting the waterfall or the spectrum on the screen. Then you have a squelch. You know the squelch. It will turn down the signal when there's nothing. You can have GUI elements, such as this GUI range, which will give you a range slider to adjust your squelch threshold. And then you have this narrowband FM receive mode. And by the way, these blue connections indicate IQ data, so radio frequency complex data. But then you have these orange connections, and that means real data. So when you run FM demodulation, you convert from radio frequency into audio, and audio is just one channel, so it's one real signal. And then you have your volume control, which is just multiplication by a constant, and your audio sound card. So in this way you can play around and you can connect different types of blocks to do your own radio transceiver if you want. GR Satellites is a GNU Radio out-of-tree module, and it contains a collection of satellite decoders for telemetry of amateur satellites. It tries to support most of the amateur satellites transmitting on VHF and UHF. And every time I do some presentation about GR satellites, I update these numbers. So far it supports 53 different protocols and more than 280 satellites. I think this is really good news because it means people are all the time launching new satellites, developing new protocols which are either variations of what existed or completely different. And yeah, the project started 7 years ago with my motivation to create decoders for some satellites we had in our bands that we didn't have any publicly available tools to decode. There is this quote on the ITU radio regulations which says that transmissions between amateur radio stations should not be encoded to obscure the meaning, and you can read that as anything which goes on the amateur radio spectrum should be open to anyone for them to use, to decode, to understand. And this is the main driving goal of GR satellites, but there are also other goals such as education. Now that we have this open source tool to decode all these satellites, people who are working on universities, for example, university satellite projects, can go in there and study how everything works. And it's also good to support new satellite teams so they don't have to start again from scratch. They can rely on these, and maybe the satellite uses some new feature, but it's just this new feature they need to develop. And it can work as well with recordings you have done, so pre-recorded files, or real-time data you can stream in from an SDR device or a conventional radio. If you have a conventional radio, you can hook it up to the computer sound card and you go. So installation, this has improved recently. If you're running on Windows, the easiest way for you to run GNU Radio, GR satellites, and some other related applications is to use Radio Conda. So Radio Conda is here. It's next kind of GUI installer for Windows. So you download this exe file and you can install it. If you Google for Radio Conda, you have the download there. Of course, the source code for GR satellites is available on GitHub, and this also kind of serves as the project web page. And if you're on Linux, we also have packages for Ubuntu and for other few Linux distributions. The usual way of using GR satellites is through the command line tool. So this is how it looks like. I guess this is large enough. So we type GR satellites, then the name of the satellite we want to use, for example here Funky1, and then we have a certain number of options depending on where we want to take the input from, what we want to do with the output, if we want any special decoding parameters. So in this simple case, I'm demonstrating decoding a WAV file, so a pre-recorded file, which comes with GR satellites. With GR satellites, you have this satellite recordings folder, which contains many short recordings from satellites, which is useful to test the decoders. And then we press enter. We will do a demo at the end if there's time. But when we press enter, we get a whole bunch of text output, and this is the telemetry contained inside the packages, inside the frames sent by the satellite. So you can see the solar panel voltage is 0 because this was taken at night, but the battery voltage is 8.1 volts, which is okay, and you have many other output I couldn't fit on the slide. You can also use GR satellites on GNU Radio Companion, so you can build your own flow graphs using GR satellites. And they can be as simple as this one, where I'm doing the same thing as before, but here I have my WAV file source. This is a GNU Radio block. Then this is the GR satellite decoder block. So it does everything, most of the work is contained inside this very high-level block. If you don't want to mess with the system, you can do this. You just choose your satellite, the sampling rate, and here you go. These are the decoded frames, so you can save the output to a file, print them on the screen in hexadecimal format. You can do any number of things, send them to another machine if you want, or whatever. And I find that people really like this approach because they like customizing what they use, and maybe they include here some spectrum display, or they include multiple satellite decoders where each of them decodes a different satellite on a different frequency. So this really gives you control about how you want to operate your station. Of course, you can dig in deeper, and what before was the single satellite decoder block, you can split that into two components. So components are like medium level complexity. And here we're splitting the work into a BPSK modulation. So FunCube does BPSK. And this will take in radio frequency and output symbols. And then we have the deframer. So the job of the deframer is to take that stream of symbols, find where the frames start, also correct any bit errors, because there is fault error correction coding on the FunCube signal, and spit out perfect packets. So there's also some CRC checking if the satellite supports that. And this is another way you can interact with the system. If you really need fine control for that, each of those two blocks we had, so the demodulator, now would be converted into all these collection of blocks, which is the way of implementing a BPSK demodulator into GNU Radio. So if you wanted and needed to do something very specific, you could change some of the really low-level parameters here. And also here we have all the steps that you need to go through in detecting the frames boundaries for FunCube, doing de-interleaving, Vita-bit decoding, Reed-Solomon decoding. So that's bit error correction. You correct any errors on the transmission, and there you go. So in this way, depending on what you're after, you can either the high-level satellite decoder block, or you can mess with the system and really customize what you do. Behind the scenes, all this is driven by YAML configuration files. So YAML is this text format for configuration, which looks like this, basically. And for each satellite supported by GR satellites, we have this configuration file. We have the name of the satellite. A satellite could potentially have alternative names. So FunCube is known as FunCube1 or AO73. We also have the NORAD ID, so the user could use any of these names or the ID to call up the satellite when they want GR satellites. Use maybe NORAD 39444. That's another way. If the satellite supports any particular telemetry servers, such as FunCube, there is the FunCube data warehouse. You can specify that in the configuration, and when you run GR satellites, it can send the telemetry there. It will also send the telemetry in general to SatNox database, but if there's another kind of third-party telemetry server, you can specify that in the satellite configuration. And then you have how the transmitters are configured. So in this case, there's a single 1K2 BPSK transmitter, and you must say the modulation, baud rate, so 1.2 kilovolts. What's the framing? So that's how the protocol is specified. And then you hook that up with the data. So in here, we only have telemetry, but there are other satellites which transmit images. So you could have telemetry and images. And GR satellites can decode those images, display the image in real time as it keeps being downloaded from the satellite. So you see the image updating line by line on the screen, and then it gets saved as a JPEG or whatever file format is being used to the disk. So those are the kinds of data you can have in the config here. Okay, next thing, changing at a rather different topic, is deep space satellites. So basically since the beginning of 2020, I've been interested in decoding deep space missions, satellites going to Mars, to the moon, and I've been building GNU Radio decoders for most missions being launched in the last couple of years. This is not really a part of GR satellites in the sense that it's not integrated with GR satellites. It's just a bunch of GNU Radio flow graphs scattered around my blog. You can read about this in my blog. But it reuses many blogs from GR satellites, so it's kind of a spin-off project. And maybe some of you have heard about amateur DSN. DSN means Deep Space Network. These are people who have their amateur stations at home. Maybe it's a 2-meter dish or 1-meter dish or even a 60-centimeter dish, and their S-band, so 2.2 gigahertz, or their X-band, 8.4 gigahertz receiver, and they try to receive probes at Mars, at Jupiter, and so on. So there are people who love to do this, and traditionally this is done only by detecting the CW carrier. So all these spacecraft signals, they have data, but they also have nice spike in the middle. So think AM modulation. It has this nice spike and then data all around. So this CW carrier, you can even see it on the waterfall when the signal is very, very weak. And that's the way that people are able to detect the signals from spacecraft as far as Jupiter or even Saturn. But for decoding, of course, you need either a larger station or the spacecraft to be near Earth. Because if you think, yeah, NASA does this daily, but they have several 34-meter antennas and a 70-meter antenna, and there's no way an amateur station is going to be comparable to that. But of course, these spacecraft get launched at some point, and also in some missions, they fly again past Earth to do a gravity assist maneuver. So in these times, the spacecraft are much closer to Earth, and you can take your amateur station and you can record, and then you can decode that data. So this has opened up a huge new world of possibilities for amateur DSM, because now you can decode and use that data. And I think that this is becoming more popular because we have more missions. I think there are many more deep space missions being launched right now than in the past decades, so to speak, especially to the moon, and also because tools are becoming more common. So when I started this, there were very few software tools that allowed you to decode these deep space missions, but now you really have the software to do it. And this is a complete different scenario. So we are used to using TLEs for Earth satellites, but for any satellite which goes outside the Earth, TLEs are no good because they are not intended to do that. And there are other tools we can use as substitutes. So for these moon missions, I always see people asking, where do I get the TLEs for this and that? And yeah, people sometimes try to do TLEs, but they are no good. So you really need to use all the tools. And I think playing with these missions gives us practical experience as a community of radio amateurs for future amateur payloads we might deploy on future missions, and even complete the amateur missions to the moon or to Mars, or there are projects. It's just a matter of time. In the future it will come. So let's better be prepared for it. As a huge help to this project, I've been getting some observing time on the Allen Telescope Array. This is a 42-dish array on California, which is specialized in SETI search. So many thanks to SETI Institute, Berkeley SETI Research Center, and the GNU Radio project for that. And I should also thank the people from AMSAT-DL who have been using the Bochum 20-meter antenna. Peter was showing this antenna earlier, for observing Tianwen-1 and many other missions. So let's see how this NASA Horizons system works. This is a web page you can access and use it to get your ephemeris information for the satellite, so where to point your dish. This is your substitute to the TLE. So this is a web page. You can go in there, you just search NASA Horizons on Google. And then you enter the search parameters. So in this example, I'm searching for Lucy. Lucy is a current mission which will study the some asteroids in the asteroid belt between Jupiter and Mars. And I have selected today as the time. Also London, England as location, because I couldn't be bothered to put Milton Keynes here. And then the table settings I have custom because I think I have removed some fields I didn't need and maybe added in azimuth and elevation. I don't know if azimuth and elevation are there by default, but anyway, you can edit and you can select the columns you want in the results. So then you click on Generate Ephemeris and instantly you will get this kind of text output, and you have a number of columns. So you have time here. Then you have right ascension and declination. So I know many people are not familiar with right ascension and declination. Right ascension and declination are the coordinates on the sky. So the stars have fixed right ascension and declination. They're not fixed on the sky as we see from Earth because Earth rotates, but each star has its own fixed right ascension and declination coordinate. So for these missions which are far from Earth, their right ascension and declination changes slowly. If you compare the position against the backdrop of stars, it moves slowly. So if you use right ascension and declination and adapt your station to control the pointing in terms of right ascension and declination, you need to do less updates. But then, of course, you can also see azimuth and elevation, and we can see, yeah, this is today in the morning, so the spacecraft was below the ground, but at some point it rises on the horizon, and it will spend 10 or 12 hours above our heads. And some other data we have, the delta means the distance in kilometers. So this is about 4 million kilometers. 4 million kilometers is not that much. So the moon is 4,000 kilometers. This is 10 times as much distance as the moon. And you can see it's decreasing, right? And this del dot is the velocity, so minus 5 kilometers per second. It means the spacecraft is approaching the Earth. You can actually use this to compute Doppler, so the spacecraft Doppler. And you can also notice that this spacecraft is coming towards Earth because, in fact, at some point during this month, it will make a flyby. So that will be a good chance to observe, even with small dishes, maybe a bear, LMB. I don't know. People have done that during launches. You don't even need a dish, just your illuminator for the feed. That's enough. Some other very good tool, if you need more advanced capabilities, is GMAT. So GMAT is an open source mission simulation software from NASA, which allows you to simulate spacecraft trajectories. So if you have the position and velocity of the spacecraft at some time instant, then GMAT will simulate the forces of gravity and other forces such as sun, radiation pressure, and so on, and it will propagate the trajectory of the spacecraft. So in that way, you can generate the same kind of data that we were seeing NASA Horizons gives to us. And you can also do other advanced things. You can simulate burns. So this spacecraft is doing a maneuver, it's burning fuel, it's changing the trajectory. GMAT can do all those calculations for you, and you can also do orbit determination. So if you have observations of the spacecraft, you have observed the Doppler or position in the sky or something, and you want to refine your estimate on this spacecraft trajectory, GMAT can do that for you. So tracking these space missions further out, it's a very useful tool, and the fact it's open source, you can just download it and use it either on Linux, Windows, or I'm not sure if Mac OS as well, is really, really helpful because the similar tools on the industry cost a lot of money and are not accessible as an amateur individual. So many thanks to NASA for making this available. Another thing I have done with these DSM projects is this Doppler correction block. And this is part of GR satellites now. So with this block, you can take a Doppler text file, and this is a very simple file. It has two columns. So on the first column, you put the timestamp in seconds. If you are doing this in real time, it's just your UTC timestamp, UTC seconds, Unix timestamp, right? And the second column is Doppler in hertz. And you can generate that file with Horizons, GMAT, or whatever. You could even use this with TLEs for low Earth satellites. But the point is, you can have any sort of Doppler description. And you can basically use this very easily. Signal comes in, you set the text file to use for describing the Doppler. You set the sample rate, and there you go. This corrects the Doppler according to the file. And then this was tested in the Allen Telescope Array by detecting the Voyager 1 signal with a single 6.1 meter dish. So Voyager 1 is the farthest human-made object. It's really, really far. I lost track. And the signal is weak, so even detecting the signal with a 6.1 meter requires precisely correcting the Doppler. You need to be within 0.1 hertz or something of the correct Doppler. So this was a good test. And in fact, I'm optimistic. The fact that with the ATA and maybe 10 minutes or 15 minutes of integration, we were able to detect the signal, means that with an amateur station, maybe a 2-meter dish or even smaller dish, if you grab the data for a whole pass, maybe 8 hours or something like that, you can detect the signal. There have been amateur radio operators who have detected Voyager, but that was a decade ago, so the spacecraft was much nearer. But I think even today that would be possible. Someone does the Doppler correction properly, has the station very well tuned, and so on. What else? So the Q100 multimedia beacon. Peter was speaking about this before. Since May, there is a new beacon on the Q100 narrowband transponder, and this uses a new modem developed by CORD, DJ0ABR. And the idea of this modem is to use your SSB channel, but be able to send as much data as possible inside the SSB channel. So to do that, it uses an 8 APSK constellation. That's a funny constellation. We will see that in a couple slides. And 2.4 kilowatt, because it needs to feed into 2.7 kilohertz, right, the SSB channel. And it's able to push about 6.2 kilobits per second, which is quite good for an SSB channel, right? So I became interested into this kind of beacon, especially since now it's 24/7 being broadcast through Q100, and I added a decoder to GR satellites using some custom blocks that I needed to develop for this kind of 8 APSK modulation, which is rather special. And the way the beacon works, Peter was showing this before, but in more detail, the beacon is basically sending two kinds of data. One is files, so you have a HTML file, which is kind of the user interface for this. And you have also the AMSAT bulletins, which are text files being sent. And then you also have some streams of real-time data. And the streams of real-time data are your waterfall data for the two Q100 transponders. So in the ground station in Bochum, they measure the spectrum, and they basically digitize it and send it through the beacon. And then the way this is all put together is very clever. So you receive this, you don't need any connection to the internet. You receive this Q100 HTML file first, or at some point. You open that with the web browser, and then there is a WebSocket server which is running on your machine that is grabbing that real-time information, the waterfall information, and your web browser, your HTML page is talking with that WebSocket server to fetch the data and update the display on your web page. So that's how, with no internet connection, you get a web page on your machine, which is showing you a live feed of the waterfalls and also the DX cluster. And so I also implemented the WebSockets part of the protocol with a very simple Python script. And I got a lot of help from Florian, DF2ET, in testing and putting everything together and demonstrating how simple it is to set it up with an RTL-SDR and GQRX from the receiving side perspective. This is as an example on the GR satellites repository. So if you go to examples Q100 multimedia beacon, you will see that. This is how it looks like. This is the example from Florian, and there are many windows in here at the same time, so let me go through them. Here we have GQRX running on the beacon, right? This is the digital beacon. This is the upper CW beacon. Maybe you can recognize it is frequency shift keying, right? And then this is the GNU Radio decoder. That's how the GUI looks like. You can see here the 8 APSK modulations. So you can notice there are 7 constellations dots around the circle, and then 1 in the middle. So in total you have 8 spectrum and so on. And I think it's really tiny in here, but this is a listing of files on his machine that have been downloaded through this beacon. And one of those files is this HTML page, which is updating the real-time information on those waterfalls, on the DX cluster, and so on. So that's how everything works together. I think there's also a video on YouTube. Yeah, this is actually a screenshot of the video on YouTube, so definitely check that out. Something else which is which interests me a lot is now we can measure the phase of the 2 digital beacons that are on Q100. We have the traditional BPSK beacon, and we have this new 8 APSK beacon, and we can measure the phase of them using these decoders. So why is this of any interest? Well, the phase difference between these 2 beacons tells us the time of flight. So that's how much time the signal spent traveling from Bochum, from the transmitter in Bochum to the satellite to my ground station, which is the receiver in Madrid, right? And yeah, there are some technical difficulties in dealing with phase, with synchronization if you want to do this with phase. So in practice, rather than using phase, we use frequency. So we use Doppler. It happens that these 2 signals have slightly different Dopplers. They are 200 kilohertz apart, so they cannot have the same Doppler. They have slightly different Dopplers. And you can measure the Doppler difference, and the Doppler difference tells you how the satellite is moving. So the satellite is a GEO, but Peter was speaking about this before. GEOs are not perfectly fixed in space. They move back and forth. We are doing a sort of 8-figure on top of the ground, so you can measure that. And to do this properly, it requires to calibrate all your frequency errors on your system. So if you're using an SDR, typically you have some PLLs on the hardware of the SDR, and you need to know about how those are set up and to compensate for the errors. And I have done examples about how to do this for Lime SDR and Pluto, which are maybe the 2 most popular SDRs besides RTL-SDR. And I could do some more examples if needed. So this is how the phase measurement experiment looks like, and we can see here the constellation of the 8 APSK beacon. This is on my station, so it's less noisy than on Florian's. I have a 1.2 meter dish, and the BPSK constellation. And then the data we get from this is if we measure just the Doppler of 1 beacon, so this is the BPSK beacon, we get a plot like this. So every day there is some kind of sinusoid curve, and every now and then you can notice a jump here. So this jump is in fact a station keeping maneuver. So every now and then, every week or so, they will slightly nudge the satellite in place to prevent it from moving too far away from its intended position. And you can see this. So this is caused by the satellite basically rocking either left or right or up and down. We will see an example. But my point is, if you do this, so the spacecraft has a local oscillator, which is being used to convert from 2.4 uplink to 10 gigahertz downlink. And if the local oscillator of the spacecraft moves, then the signal you receive will also move. So all these ugly things on the evening are the spacecraft local oscillator moving. If we want to use this to understand the satellite orbit, it's not very good because we have this contamination by the spacecraft local oscillator effects. But however, if we compare the Doppler of the two beacons, then the local oscillator is the same for both of them, so the effects cancel out. And we get this very nice picture where now the units here, rather than hertz, they are meters per second. So the satellite moves at a speed of a couple meters per second, really. And you can see that there are no more weird oscillations. There are some glitches, and this is an issue with my system. I haven't really troubleshooted properly. I haven't spotted where the glitches come from. But these data can now be used to understand the satellite orbit. And we can fit this into GMAT and use orbit determination. So what GMAT will do is to try to find the best orbit that fits our measurements. And this is the residual, which is the error we get. So this is the difference between what GMAT has been able to achieve and what we have measured. And the difference can be measured in basically centimeters per second. So this is 2 centimeters per second. You can see there is a slight wobble. So it means the GMAT orbit is not perfect. There are some effects which are not being captured too well by the GMAT model. And then you can see this display where the motion of the satellite is decomposed into its components. So in blue you can see the satellite radius. So basically it's going up and down, so away from Earth towards Earth, 20 kilometers in this case. So it goes 20 kilometers up, 20 kilometers down every day. It repeats. In orange you can see the z-axis, so that's north and south. It travels 70 kilometers north, travels 70 kilometers south. And then in green you can see the longitude, so that's east and west. It travels 0.1 degree, I think. Yeah, 0.1 degree east, 0.1 degree west. And in longitude it will tend to drift towards the east until they sort of correct that with a station keeping maneuver. So why can this sort of data become important? Well, if people are trying, as Pete mentioned, and as you will see later on, to push the boundary of what is possible and trying to work the satellite right from the footprint or even beyond, then you might need to know this. You might need to know when the satellite is actually moving slightly towards your location, because maybe you can only work it when it moves 0.1 degrees towards you. So this can make the difference between being able to operate or not if you're on the footprint edge. And if you try to use TLEs for this, they are no good at all, because TLEs for geostationary satellites are very difficult to do properly. So we as amateurs can only get this kind of data by doing our own measurements and our own orbit determination. Of course, SGEL as a company has this kind of data, but they won't share. So this is something we can do. There are more stations needed to do this properly, because if I have my station in Madrid and I have Bochum at the transmitter, I'm not able to determine if the satellite is moving away from Earth or down south, because in both cases the distance of propagation increases. So there's some sort of variable we're not able to discern with just 2 stations. If we had station on the southern hemisphere, then of course we can measure the difference. So what else? Yeah, I think that's the last slide. So let me do a GR satellites demo really quickly. I guess most of you are familiar with this SatNox webpage. So what I'm going to do is to download an observation from SatNox and try to decode that with GR satellites. The first thing I'm going to do is to filter observations which are good, because by default we have all these observations scheduled in the footer. So we only want these green good observations, and then update. We don't search for a particular satellite. So update, yeah. And then BisonSat, I think we have that. So let's try. What we want to get at is the audio. So there's the, where's the audio link? It used to be here, right? Yeah, maybe this hasn't been uploaded. Let's take this one instead. Yeah, audio. This is kind of the live demo, which might go as expected or might not, but even so copy link. And then I'm basically going to download. So you can download any way you want. This is an OGG file, recording of the audio of the BPSK signal. And then once we have this file, so we have these SatNox, blah, 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 OG, then GR satellites. And the satellite is called Xiaonian Xing. So this is, I think I need to do Xiaonian Xing. So this is a Chinese satellite. And then we can do WAV file. Even though this is all GR satellites can open a few different sound formats, and it will run. And in this case, it doesn't decode anything because, this is live demo. But now you can troubleshoot and see, is this signal well captured? Is there too much interference? Maybe there's some offset or whatever. So let me try to demonstrate with FunCube. It's a FunCube recording or something. Yeah, so for FunCube we can use just AO73 WAV file and then satellite recordings AO73, and then we run this, and immediately, because it's a recording so it can go through really quickly, and this is just a couple of frames I think, you get this packet from BPSK downlink, you get all the telemetry. So this was what I was showing earlier on the slide. So basically the usage is like this, and for troubleshooting the examples that do not work, such as this Xiaonian Xing, you can dump more information, make plots, and try to see why there's a problem with decoding. And that's all I had. Thanks.
Okay, thank you very much. Our appreciation. Very thought-provoking, that is. It got it right till you went on geostationary satellites. I didn't realise they move so much. That was really something. Have we got any questions from the audience, please? Don't look stunned. Someone's got a question. David.
You were talking about 8PSK. Sorry, Chris. You were talking about the new beacon on QO100 using 8PSK. Do you think that format works particularly well on that satellite because it is on 10 gigahertz, it is relatively stationary? How do you think that modulation format would work in low Earth orbit where you might be going through an auroral zone? Too much phase shift or possibly okay?
Yeah, I'm not sure. That's a very good question, because on Q100, one of the things you have is the phase noise or frequency stability, if you wish, of the downlink of your LNB, because many people don't have a GPS locked receiver. So you need to design a waveform which is able to cope with that, and this 8PSK manages to do so in a really good way. Then the question of, you have a low Earth orbit satellite, it's going through auroral, there are phase shifts. I guess that depends on the frequency, and yeah, no idea. Would have to do some estimates or some models. No idea from.
Need to get one there and try it.
Yeah,
okay.
Potentially.
Okay, thank you. Has anyone else got any more questions?
Yeah. Oh, I'll just shout. I'm quite surprised. All right. Okay, probably for other users. I'm quite surprised that you can, well, particularly deep space network, you can pick them up with amateur equipment, because I would have thought they'll adjust their data rate according to the signal-to-noise ratio. So if they turn up their data rate to make the best use of their signal-to-noise ratio, you won't stand a chance. Or maybe they don't change it as much as I think.
Yeah, that's a fair point. So what happens is, on the launch itself, the spacecraft is going to be very near Earth for just a few days. And they don't have any mission data so far, because if you want to go to Mars and graph your data, then you engineer your system to transmit data from Mars, not from Earth. So when they launch, they typically run at the lower or normal data rate. They could do much faster because they have very large antennas, but why bother? And also, what they do is to cope for the unforeseen. So they have these safe modes where they transmit data really, really slowly, just in case the satellite is not able to orient its antenna properly. Also, when they launch, they typically don't use the high gain antenna. So yeah, the first week there's nothing special designed for that, and it's a regular or even lower speed data rate they use.
Thank you. Are there any more questions from the audience?
I just wanted to first of all say what a brilliant tool that is and how inspiring a lot of your examples have been on the web. That you poured a load of time into, like the Voyager decode, and for many of us that's the only sort of time we've ever seen how it works. So I wanted to say thank you for that, and also wondered how you how this all fits in with your professional work, because it seems like a full-time hobby, which we all know is a problem.
Yeah, thank you. So the question is how this all fits with my profession. And yeah, sometimes it's difficult to find the time. So I have a full-time job working in the satellite navigation industry and do this as a hobby. And it's difficult, but I mean, you're also seeing the result of years and years of doing this. So if you put a small amount of time, not every week, but most weeks throughout the years, eventually you gather a large amount of things, right? Thank you.
Do we have any questions from the stream?
I don't think so at this time.
All
A
dumbfounded.
lot of congratulatory messages.
Well, yeah. Any others in here? Anyone else?
Just a quick one. Can you run this on a Raspberry Pi?
Yeah, the question is if you can run this on a Raspberry Pi, and the answer is yes. For installing it on a Raspberry Pi, I think you can even use Conda. So Conda has images for ARM, or even if you run Ubuntu on your Raspberry Pi, you can, yeah, there's the Ubuntu package also for ARM and ARM64, if I'm not confused. So definitely, yeah.
One more. Ian.
Yeah, on that topic, presumably GR satellites might also be part of PyBombs, so I can install a pair of PyBombs.
Yeah, GR satellites is also part of PyBombs, but the GNU Radio community is kind of moving away from PyBombs. So
but yeah.
what they say is if PyBombs works well for you, then go ahead and use it. If it doesn't, then you might not have people helping you.
Yeah, that's not a problem.
Okay. Well, show our appreciation again. Thank you very much.
Thank you.
Very good.